Today we are going to start with design. So we have mainly three aspects of design of assembly and packaging. And the first is electrical design. The second would be thermal design, thermal management. And the third is reliability of assembly and packaging. Now let's have a look at electrical design, and we start with something very basic. Normally we think electronics are fast, but the maximum speed of electronics we can have, or the speed of a signal, can be the speed of light. On the other hand, if an electromagnetic wave is moving inside a medium, that medium in the easiest case is characterized by the permittivity and the permeability. Both describe the increase of the respective electrical or magnetic field strength. Taking both as a product, and you can say the square root of permittivity or relative permittivity times relative permeability is the so-called refractive index. So the refractive index describes when an electromagnetic wave enters such a medium, how much that beam is deflected. So by the refraction process. On the other hand, the basic reason of this refraction is that the speed of an electromagnetic wave in its propagation is slowed down. And typically you can say the speed of an electromagnetic wave is the speed of light divided by that refractive index. So you could say the speed of a signal is the speed of light described by the square root of that refractive index when, as in most assembly cases, the permeability is 1. Permeability is not 1 when we are near a magnetic material like, for instance, nickel. The speed of light is roughly 300,000 kilometers per second. So you could also say it's roughly 0.3 meter per nanosecond. And that means when you have a computer operating at a very high frequency, somewhere in the gigahertz range, where the cycle time is 1 nanosecond, you can have already effects of the speed of that signal, and the running time of a signal, or the so-called time of flight of a signal, will have an effect. The second is when a signal, which always has an electromagnetic wave around it, is moving into a certain direction on a conductor path, the voltage will never directly go from 0 to 1, or as we have in TTL level, from 0 to 5 volt, or from 0 to half a volt, like in a modern computer. But there is a leading edge of that signal. Typically, the leading edge is measured between 10% of signal rise and 90% of signal rise. Also, such tolerances determine the switching points of electronics. And so that initial length is the so-called edge length of that signal. If you just take, let's say, a snapshot of that. On the other hand, the time of the edge, of course, depends on the speed of of that signal. So you could again say the speed is just the LH it's depending on the relation between LH and TH. So if we have a longer rising edge, of course it will also take longer until the signal comes from that position to the next position. So also turning that round, you could say the leading edge is the rise time multiplied with the speed, and that again is the rise time times speed of light divided by the refractive index, and that is the rise time times speed of light divided by that permittivity of the material. And now there is a rule that says when effects of rise time and when effects of speed of the signal have to be taken into account, of course, that is an important part of the design process. And to decide whether that is necessary, we use the so-called transmission line criterion. And that says when the length of the track is longer than a certain threshold value, when it's longer than half of the leading edge length of a signal, then the track behaves as a so-called transmission line. That means in that case, the line length is relatively long compared to the rising edge, and the signal behavior must be optimized. And typically, for digital signals, there is a simple rule that says the rise time of such a signal is roughly 7% of the clock cycle time. So if we have a clock cycle time of 1 nanosecond, that would mean we have 70 picoseconds of rise time, or we can take 7% of the inverse of the clock frequency. So when you make a design, you can make an assumption what's the clock frequency of my ASIC or microcontroller, and in that way it's relatively easy to estimate if this transmission line criterion is met, and if you have to do an optimization of your behavior of your line. Okay, this limiting condition, for instance, yes, you can just take that formula, and that means when the track length is longer than 7% of speed of light divided by twice the clock frequency and divided by the permittivity, then you get that criterion, and when the track is longer, then you must take measures. In the previous formulas, we had the so-called effective permittivity. Why is it the effective one? For instance, when we have a conductor and that conductor is placed on a substrate, here, for instance, we have air, and here, for instance, we have epoxy or aluminum oxide or so. So you could say in cases where we have such coplanar tracks, the permittivity is the permittivity of air, which is 1 plus the permittivity of that epoxy, for instance, and you take the mean of both, and so it's epsilon r plus 1 divided by 2. Of course, if it's covered with another material, it could be not a 1, but epsilon r1 plus epsilon r2. If the line is just inside that medium, of course, the effective permittivity is just the permittivity of that medium. So that would be a case like that, for instance. For so-called microstrip line, which is more complex, which we can see on the next page here on top, we can say the formula is more complex. Of course, you do not have to keep it in mind, but for coplanar tracks, you should be able to estimate that permittivity. Okay. Now, for such typical cross sections of a conductor, so for the microstrip line or for the strip line where the conductor is embedded between two ground planes, we can also give other data. And one is the capacitance. And that index L means always per length. Also, we have the resistance per length. So that is, in that case, proportional to the specific resistivity divided by the width of that conductor and the thickness of that conductor. Here we can see that's the width, and that's the thickness. And in that way, the resistance can be computed easily. Also, we have a so-called conductance, which we will see in a second. And such conductor also acts like a coil. And in that case, we can say the inductance per length is it can be computed, but the easy thing here is the inductance and the capacitance are inversely related. So typically, if capacitance is high, inductance is typically low, or if inductance is high, capacitance is low. That's important. So in many cases, we use either capacitance or inductance, but all we have to take into account. Unfortunately, I was not in the complete order. If we take the equivalent circuit diagram of a transmission line and take it only for a certain short element of that line, we have the serial inductance, as we have seen it. We have the serial resistance, and we have a parallel capacitance. So we can see here it acts like a plate capacitor, and we have a ground conductance. That is not really a DC conductor, but it is an AC conductor. And the main reason it acts is that that conductor acts as by the recharging of that capacitor. So always when we load that capacitor and uncharge it, we have the so-called dielectric losses. And these losses increase with the frequency of our signal. They increase with the so-called tangents delta, that's the loss angle, and they increase with the capacitance per length. And that means that conductance is really a high frequency problem. It's not a DC problem, but for instance, when frequencies approach hundreds of megahertz or even hundreds of gigahertz, then it can be a severe problem. And we have already seen this loss angle, tangents delta, is typically between 1 promille and 1%. So having such an element, that means when a signal comes here and it propagates, it is slowed down by this inductance. Also, that resistor will lead to a slow charging of that capacitance, and also the conductance will lead to even slower charging, because also a certain part of that current is lost. And in that way, when we have a signal, that signal will come with a certain speed here. The speed of that signal can be computed, and as the main thing is when the signal comes along that line, the signal charges up the conductor, or it charges the conductor and builds up an electrical field between the ground and this conductor line. And you can say the current you have here for charging a certain length of your material is proportional to the length times the charge you can have per length and the time it takes. So always current is change of charge per time. And so you could say that's just the charge per length times the speed you have here. On the other hand, the charge per length is proportional to the capacitance per length and proportional to the voltage you use here, for instance, 0.5 to 5 volt in typical electronic logic. And in that way, you can still replace the speed by speed of light divided by refractive index, and that leads to the conductor's impedance. The impedance is just voltage divided by current, and so you take the current, put it here, and so the impedance is just 1 divided by the specific capacitance and divided by the speed, and so it's the square root of that effective refractive index divided by the capacitance per length and divided by the speed of light. And so you could say the impedance is mainly affected by the geometry of a conductor line, because that permittivity is again a factor in that capacitance per length. So in that way, you know the impedance of that line, and so such a line has impedance which is independent of the length of that line. So now when you look at the wiring time, so that's typically the time of flight of a signal plus the time the time of the rise of that signal. And when you say the time of flight is just L track times square root of permittivity divided by C, and this second time, which is due to the RC element behavior, then that can be described by the RC circuit. That's a resistance per length times the capacitance per length times the length square, because R is RL times L and C is CL times L. And in that way, we have the properties of that line and the wiring time, so that's the total time a signal needs, is increased with the square of the length of that line. In case we have a driver which has a high resistivity, then we can say we have that second RC term, but also we have the influence of the driver times the capacitance of the line times the length of that track as an additional factor. And in that way, we can also estimate what the time is which that is used by a signal when it passes a conductor of a certain length. Here again, for that second case, we see we have that driver which drives the signal to our conductor lines, and in that way we can estimate these properties. There is one more phenomenon of assembly and packaging which is important. When we have a conductor and that conductor has a certain length, and when a signal propagates, of course we would expect that that signal would run all through our circuit, but that is not the case. Due to the current here, we have Lorentz force on the carriers, and that leads to the fact that the carriers are only conducting in the outside of that circuit. So that's a so-called skin effect. So here we have the skin of conduction, and that is conduction free. So that can be just explained if we have a current here. We have eddy currents, and these eddy currents will make the carriers move out of the middle of that conductor. The skin depth is proportional to the square root of the specific resistivity divided by the permeability, which is the absolute permeability, and divided by the frequency of our circuit. And in that way, especially for high frequencies, the skin depth is only very small. So skin effect is more important for big cross sections of a conductor, but also in small ones it can have an effect. The resistance per unit length of a conductor is now, when we combine that, proportional to the specific resistivity times the square root of frequency times permeability divided by the width of that conductor and divided again by the specific resistivity. It must be noted that especially in magnetic materials, that skin effect is significantly larger because the relative permeability can be, for instance, like 100. Then that means the skin depth is only 1/10 of the skin depth in a non-magnetic material. And in that way, skin effect already has an effect in conductors of large cross sections like high voltage power lines, and that's one of the reasons why people now tend to install high voltage power lines which are carrying direct current and not alternating current anymore. Okay, so we have seen the principal effects of assembly and packaging on the electrical behavior, and we must say we have three physical phenomena. One is resistance, second is capacitance, and the third is inductance, which all can have an effect on the strength and the speed of signals in our assemblies. Okay, here is an example that was provided by Dr. Quay. For instance, we have a high frequency IC, for instance, in the 100 gigahertz range or so. So we can say we come with a modified transmission line. The wire bond, when we come towards the IC, is again modeled as symmetric or almost symmetric RLC network, and on the outside of that circuit again that must be modeled in that way, and then the signal goes along a modified transmission line. Okay, in that way we can determine whether it's important if assembly and packaging has an effect on the electrical properties or not.